Welcome to Unique Academy YouTube channel. So in this video, we will see gate problems from thermodynamics. Okay, so question number 1, a system with rigid wall. So this is an important point here. So that is a constant volume system. So this is a system with rigid wall, a volume constant system. Is at a temperature T1. It is used as the heat source for heat engine, which rejects heat to the reservoir maintained at T0. The specific heat of the systems are constant. The temperature of the system finally reduces to T0. So this temperature from T1, it reduces to T0. The maximum work recoverable from the heat engine. So that means by removing the heat from here, Q1, operating in a cycle, maybe a maximum work. That means it is a Carnot heat engine. So it is a Carnot, not Carnot, reversible heat engine, because Carnot means your source is at a constant temperature. Similarly, sink also at constant temperature. So you cannot say that it is a Carnot cycle. It is a reversible cycle. Reversible engine. So that it produces the maximum work output. And it rejects the heat with the surrounding temperature T0. Okay, so a system with rigid wall is initially at temperature T1. It is used as a heat source for a heat engine, which rejects heat. So the heat engine rejects the heat to the reservoir maintained at T0. So what is the maximum work recoverable from the heat engine per unit mass of the system? So the maximum work will be Q1 minus Q2. So we know that this closed system, maybe you can see that so the heat is removed from the system, Q1. No work transfer. So it is a closed system with volume constant. So there will be a change in internal energy, U2 minus U1. Change in internal energy. Maybe you are reducing to atmosphere. So because the temperature of the gas inside the closed system is reduced up to T0 to get to the maximum work output. So U0 minus U1, final minus initial. So applying the first law of thermodynamics, Q is equal to work plus change in internal energy. Work will be 0. So heat transfer is Q1, which will be coming out, so negative. The heat is going out, so negative. Then Q1 will be equal to U1 minus U0. So negative I have taken in the other side. So this will be per unit mass of the system. So T1 minus T0. This is your Q1. Now you have got Q1. So what is, how do we get Q2? So what you do, you take the entire system as a universe. So we know that for reversible engine, entropy change of the universe equal to 0. So here three systems are there: system 1, system 2, system 3. So change in entropy of system 1 plus change in entropy of system 2 plus change in entropy of system 3 is equal to 0. Change in entropy of system 3 is 0 because it's a cycle. A reversible heat engine is a cycle. So for a cycle, property change will be 0. So the system 1, the entropy, it is losing entropy. Entropy change for a closed system. So that maybe you know that dq by t. So entropy change ds equal to dq by t. So dq for a constant volume cv dt by t. So it's a constant volume. So volume constant. So dq is cvt. So change in entropy. Maybe here it is change from 0 to 1. This is the change. Is equal to Cv ln final temperature T0 by T1. So here T0 is less than T1. So this is the entropy change for the constant volume system. Cv ln T0 by T1. So entropy change of system 2. System 2 is a thermal reservoir. It is getting the heat. So positive reservoir Q2 by T0 equal to 0. So Q2 will be equal to minus T0 into Cv ln T0 by T1. So Q2 will be made minus sign if you take it there. So Q2 into Cv ln T1 by T0. So this is the heat transfer. This quantity will be positive because T1 is greater than T0. So the heat rejected. Heat. So the maximum work now you can get it. So the maximum work will be equal to Q1. Q1 is Cv T1 minus T0 minus Q2 is T0 ln Cv T1 by T0. Cv ln T1 by T0. So if you take Cv outside, T1 minus T0 minus T0 ln T1 by 0. So this is the maximum work. So answer is A. So A is the answer for this question. So sometime, if it is asked, the heat is taken from the source, which is at constant pressure. maybe I just, so heat is taken from a source. Maybe T1, it is reduced to T0 by a pressure constant process. So the heat supplied and a heat engine, reversible heat engine. So it gives you maximum work output Q2. It is rejecting the heat to the atmosphere. So this is the atmosphere. Now here Q1, you know that constant pressure heat MCP, T1 minus T0. So constant volume, it is MCV, T1 minus T0. Constant pressure, it is MCP. So the maximum work is equal to Q1 minus Q2. To find Q2, you need to take the entropy change of the universe. System 1, 2, 3. So entropy change of the universe equal to 0 for reversible. Because the heat engine is reversible, so the inverse, everything is reversible inside. All the systems are operating reversibly. So entropy change of the universe, entropy change for 2 plus entropy change for 3 equal to 0. Entropy change for 3, 0 because it is a cycle. Entropy change for 1, so it is dq by t from 1 to 0 plus delta 2, delta S2 is Q2 by T0 because the reservoir 2 is receiving the entropy, so positive. So this gives you Q2 by T0 is equal to minus 1 to 0. This is MCP dt for a constant pressure heat rejection. 0 to 1, that is constant pressure heat rejection. Ln T0 by T1. So Q2 is equal to, the minus sign you can take it inside. MCP ln T1 by T0. This is heat rejected. So now MCP T1 minus T0 minus T0 T1 by T0. So if you take MCP outside, so this is the maximum work. When the source giving the heat at constant pressure. Maybe this is not asked. So sometime there is a possibility that the question can be asked in this aspect. So now we move to the next question. A reversible heat engine operating between two reservoirs maintained at T1, T2. T1. So T2 work out. So two reservoirs maintained at T1, T2. So this will be the Carnot heat engine then. T1. So this will be the Carnot heat engine. So which is the more effective way of increasing the thermal efficiency? We know that the thermal efficiency for a Carnot is T1 minus T2 by T1, which will be equal to T2 by T1. Now let us see. Increasing T1, keeping T2 constant, will increase the efficiency. From this formula, so this will increase the efficiency. Increasing T1, keeping T2 constant. So decreasing, second option, decreasing T2. Decreasing T2 while keeping T1 constant will not increase the efficiency. Increasing T2 while keeping T1 constant will not increase the efficiency. Maybe from this formula you can just understand mathematically. Decreasing T2 while keeping T1 constant. So there are two options which will increase the efficiency. But which is a more effective way of increasing that? Maybe we will take A first. So A, we take it efficiency 1. So what is that? Increasing T1. So what you do, 1 minus T2, you keep it constant. T1 increase by an amount delta T. So increasing T1, delta T. This is one thing. D, efficiency 2, you take it efficiency 2. 1 minus here, you are decreasing T2, same delta T amount. You decrease delta T, same delta T amount, keeping T1 constant. Now you try to calculate this efficiency 1 minus efficiency 2. Let's see what you are getting. So 1 and 1 will be getting cancelled. So you get T2 minus delta T by T1. T2 delta T. If you take LCM, so this 2 will get cancelled. So what you get is, if you take maybe delta T is a small amount. Delta T is a smaller quantity. So you can neglect this. So you can neglect delta T square. Neglect. Because we assume that there is a small increment in the temperature of, so delta T is a small increment. So square of that will be very small, so you can neglect that. So now what is remaining is delta T, if you take it, it will be T2 minus T1 by T1 plus delta T. So now we know that T1 is greater than T2. We know that T1 So that means efficiency 1 minus 2 is negative. So this indicates that delta 2 is greater than delta 1. So more effective way of increasing the efficiency is to decrease delta 2, decrease D2, T2, keep T1 constant. So the answer is D is your answer. So your answer is D. Now we move to the next question. So a particular gas sample is initially maintained at, so initial volume 600 centimeter cube. So this will be 600. So we know that 100 centimeter equal to 1 meter. So 10 power minus 6 meter cube. So we wanted in meter cube. So this you can take it 6 into 10 power minus 3 meter cube. So V1. And your pressure P1, 100 kPa. It is compressed during a quasi-static process following relation PV squared is equal to constant. So a gas is compressed. That means it is a piston cylinder device. So it is a piston cylinder device. So it is compressed. That means you are giving the work, maybe a process 1 to 2. So here you have internal energy change. We don't know the heat transfer. So which direction the heat transfer? There must be a heat transfer. So it follows the relation PV squared is constant. PV squared equal to constant. This is the relation it follows. So what is the work transfer? The compression is continued till the volume become 2000 centimeter squared cube, final volume. So this will be 2 into 10 power minus 3 meter cube. The magnitude of work transfer in kilojoule. So work transfer, we know that for a closed system, integral 1 to 2 PdV. So we know the relation P equal to C by V squared to dV C V power minus 2 plus 1 minus 1 minus 1 by V. So this you can so C into 1 by V1 minus 1 by V2 after substituting the limit. So C we can take it maybe when it comes to here, C can be P1 V1 squared or P2 V2 squared. Both you can take it. Maybe P1 V1 squared by V1 minus P2 V2 squared by V2. So this will be, so your work transfer is in 1 to 2. Work transfer in the process 1 to 2 is P1 V1 minus P2 V2. So P1 V1 V2 is there. So since it is asked in kilojoule, so we can substitute, maybe very carefully you have to see, this will be in kPa, this will be in meter cube. So that these two together will be in kilojoule. Unit must be carefully put. So now we get from this equation, we get P2. So P1 from this equation we can get P1 will be 100 kPa. V1 is 6 10 power minus 3 square. P2 is what we want. V2 is 2 into 10 power minus 3 the whole square. Okay, so P2, which will be which you will get in kPa. (900 kPa). So now you substitute those here. P1 is 100. V1 is 6 into 10 power minus 3 minus P2 is 900 into P2 is 2 into 10 power minus 3. So this for transfer. So minus 1.2 kilojoule. So this negative sign indicates that the work is given into the system, because integral PdV will give you a positive sign if the work is coming out of the system. Since work is going into the system, or it is compressing the gas, so work is given into the system, so negative sign. So answer is 1.2 kilojoule. 1.2 kilojoule. Okay, so now we move to next question. So a carbon dioxide enters an adiabatic rigid nozzle. So you have a nozzle. So this is the nozzle. Nozzle is a steady flow device. So you have a entry and exit. So it is at 1 MPa and 500 degree. So the pressure at the inlet is 1 MPa, temperature 500 degrees centigrade. The mass flow rate. So mass flow rate is same at inlet and outlet because it is a steady flow device. The area, inlet area of the nozzle, 40 centimeters squared. That is 40 into 10 power minus 4. Because you know that 100 centimeter is 1 meter. So 10 power minus 4 meters squared area. So the exit velocity V2 is 10 times V1. If CO2 is considered as an ideal gas, so this is an ideal gas with the gas constant or the ratio of specific heat gamma. So gamma is given, R is given. What is the exit temperature? So now you apply the steady flow energy equation. That is energy in equal to energy out. So energy in is only the enthalpy. So H1 Then you have a kinetic energy, V1 squared by 2. Potential energy is nothing is said about potential energy. So potential energy we will neglect. Maybe I write just for the sake of writing. Mass flow rate is given, and since the okay, we need not to be multiplied by the mass flow meter because uh, we need not to multiply per kg because we want only ultimately the temperature. So the outlet will be, so it is not a work producing device or work consuming device. So no work transfer. So, and nothing is said about the heat transfer. So we can assume that, okay, it's adiabatic. So adiabatic. So you have no heat transfer plus G is at 2. So now the potential energy is neglected. So this will be 0. This will be 0. So since it is an ideal gas, so H can be written as CpT1, velocity V1 squared by 2 is equal to CpT2. Velocity V2 is 10 times V1, 10 times by 2. So to find out that we need Cp and V1. Cp and V1 is known, then you can find T2. Cp we can find using, so we know that for an ideal gas, gamma R by gamma minus 1 is Cp. Gamma is 1.29. So R we substitute in, because velocity is in meter per second. Whenever velocity is in meter per second, that means it is joule per kilogram. When velocity is in meter per second, this time will be joule per kilogram. So Cp must be in joule per kilogram Kelvin, not kilojoule. Temperature must be in Kelvin, not in degree centigrade. So in this case, the temperature must be in Kelvin. So you substitute R 190. Okay, 0.19 kilojoule per kilogram Kelvin becomes 190 joule per kilogram Kelvin, gamma minus 1. So 845 joule per kilogram Kelvin. Okay, Cp is known. So now velocity. So how do you calculate velocity? So mass flow rate. From the mass flow rate, rho1, k1, v1. Rho1 is p1 by r t1, a1, v1. So m dot. Now you substitute m dot is 1.5. P1 is 1 MPa, so 1 into 10 power 6 Pascal. So this is 1 into 10 power 6. Pascal is Newton per meter squared by R. R you must substitute 190. Temperature. Temperature must be in Kelvin. 500 plus 273. 773 Kelvin. Area is in meter squared. 40 into 10 power minus 3 into V1. So we get V1. So 5.5 meter per second is V1. So now everything is known. So Cp is 845.2. T1 is 773. V1 plus V1 is 5.5 squared by 2 plus, sorry, equal to 845.2 into T2 plus 10 times V1, 55. So now T2 you will get in Kelvin. Seven 71.23 Kelvin. 0.23 Kelvin. So you have to write in one decimal place. So that is 771.2 Kelvin. So that is the answer. So now we will move to the next question. So a closed system containing 8 kg of gas. So you have a closed system containing a mass 8 kg undergoes an expansion process. So that means the work is outward. It follows a process PV power 1.2 constant. The initial and final pressure 1 MPa. Final pressure. So expansion, so 5 kPa. Maybe this you can write in kPa, 1000 kPa. Well, initial volume. So V1 is 1 meter cube. The specific internal energy decreases by. So that means, so U2 minus U1 is decreases. Initial internal energy will be more than final internal energy. So 40 kilojoule per kilogram. It is a specific internal energy. So U2 minus U1. Minus sign is because internal energy decreasing. The heat transfer associated with this process. So now we can apply the closed system, the energy equation. So first law of thermodynamics. Applied to closed system. for a process 1 to 2. So that is Q1 to 2 is equal to W1 to 2 plus change in internal energy. So we need W1 to 2. It is integral PdV from 1 to 2. So maybe we know that the process is given. So we will take it as PV power n equal to constant, where n is 1.2. So this we take it and substitute here. It is C by e power n dV, integral 1 to 2. So C is constant. So V minus n plus 1. Substitute 1 to 2. So you can write C equal to P1 V1 power n or V2 V2 power n. So you can write in any way. So this, if you see, maybe 1 by 1 minus n into C. V2 1 minus n minus V1 1 minus n. So this can be written as E2 V2 power n, E2 power 1 minus n minus E1 V1 power n E2 V2 1 minus n. So you have got P1 V1 P2. So we need V2. So for that we use this equation from here. P1 is, maybe we will substitute in kPa itself so that the work transfer we will get in kilojoule per kilogram. Okay, so if you substitute this P in kPa, V in meter cube, so that this you will get in kilojoule. So unit, you should be very, very careful. So let us substitute this. P1 is 1000 kPa. V1 is 1 meter cube, 1 power 0.2. P2 is 5 kPa, V2 power 1.2. So we want V2. So 82.7 meter cube. So now you get to the values. So W1 to 2. Substitute those values. P2 is 5. V2 is 82.7 minus P1 is 1000 by 1 minus 1.2. So this much kilojoule. So 2932.5 kilojoule. So you have got the work transfer and internal energy change is given. So work transfer will be positive because it is an expansion. So you got in the integral PDV as a positive value. So in kilojoule, 2932.5 kilojoule. It is in kilojoule. Change in internal energy. See, internal energy decreases by, so negative sign. Internal energy decreases, so negative sign. 40 kilojoule per kilogram, so multiply by mass 8. This will give you the positive heat 2612.5 kilojoule. So heat transfer is positive. So that means heat transfer is given into the system. So work transfer is 2932.5 kilojoule. Heat transfer is 2612.5. Your internal energy change U2 minus U1 is equal to minus 320 kilojoule. Now, if you look at that for this process, PV power 1.2 constant. So the work transfer W1 to 2 is more than the heat supplied. So the work is extracted not only from the heat that you supplied, but also from the mass inside. So the internal energy of the mass is also extracted work. So the expansion work, it is not only taking the heat, but also it is extracting work from the mass of the system. That is why the work output will be more than the heat supplied for this polytropic process. So the temperature reduces. Maybe we will just, so now the answer is only what is asked is the heat transfer. So that is 2612.5 kilojoule. Now just see, so we will try to differentiate a constant pressure process as well as this polytropic process. Maybe just have a bit understanding. So from the PV diagram, so if you have a constant pressure expansion, so it is 1 to 2, constant pressure expansion. This is the constant pressure expansion. So that N equal to 0. Whereas TS diagram, it will be something your pressure constant expansion 1 to 2. N equal to 0. N equal to 0. So this is the constant temperature. N equal to 1. Temperature constant process. This is PV power N equal to, maybe N equal to 1.2. Any value, maybe there will be a limitation. C is N equal to gamma 1.4. So up to that we are talking about. So here N equal to 1, n equal to 1.2. So what happened? The expansion process in the, if you see your pressure constant process. So expansion, you get the work output. So you supply the heat. So there will be internal energy change. Since the temperature is rising, you see the TS diagram for the process, maybe this, for the process n equal to 0, the temperature is rising. So the internal energy is positive. That means internal energy to be positive means the heat supplied will be more than the work output. So heat supplied will be more than work output, so that internal energy change will be positive. Whereas for the polytropic process, PV power 1.2 constant, what we have seen. So there is a work transfer. So there will be a heat transfer. There is an internal energy change. Now you see 1 to 2, the temperature is reducing. For a polytropic process in the TS diagram, PV power n equal to constant n 1.2, the temperature is reducing. So temperature is reducing, so this will be negative. When this is negative, so work output will be more than the heat supplied. That is why U2 minus U1 will be less than 0, negative. But whereas if you take constant temperature constant process, so there will be a heat transfer. So here U2 will be equal to U1 because you see the temperature is constant. So the temperature is constant. So all are expansion, all are with respect to expansion. So expansion process, not a compression process. Compression process, things will reverse. So everything will reverse. Heat will go out, work will come in. Okay, so now we only talk about the expansion process. So in this case, what happened? So heat supplied will be equal to work out. Internal energy U2 minus U1 change will be 0. Okay, so this is what is the difference between the three processes that we need to understand a little physically. So now we go to so thank you for watching this video. If you are happy with this video, please subscribe the channel and share this video to your friends who are preparing for GATE mechanical engineering subject. If you want to join for the GATE 2026 video course, please contact in the number mentioned and you can see the website. Thank you.